Well, we have made it now to our last section, or the last section we're going to do anyway, in Chapter 7, and we are working on a different base this time. We are working on something called base E, and E is actually a new number for you, and yes, I did say that correctly. It is in fact a number, just like pi is a number. It was named after someone. We'll talk about it in just a second. But we're going to talk about a different base. So instead of like base 10, which is the common log, we're going to talk about base E and something that ends up called the natural log. All right, so we've got this number E. It's an irrational number. Like I said, the best thing I can compare it to is pi, just because it's a known value. It's something that we have in our calculators, and it's not like just 3 or something like that. It's a more complicated value than that, and it has a meaning deep within math somewhere. So our natural base E is approximately 2.71828, etc. All right, so that decimal keeps going, just like pi's decimal keeps going. Let me show you something really quick in case on your calculator you have ever wondered what that button is right there. We've got 1, then the 10 to the x, then the e to the x. It actually is a value. So if you type in just e, you have to do e to the first. So that's your approximate value that you get. So you can square it, you could take the square root of it, you can do anything we want to e, but what we're going to do right now is use it as the base in a logarithmic function. Okay, so the next thing we're going to talk about is the natural base functions, or these natural log functions. And we're going to look at a graph really quickly and then talk about some properties and stuff like that. So the natural base, the function e to the x, so we can use e as a base of an exponential function, and then we can also use it as the base of a logarithmic function. Okay, so if we look at this first one. So e to the x is just your run-of-the-mill exponential function. If you plug in 0, you get 1. Remember, all exponential functions have the point 0, 1. And then if you plug in 1, e to the first gives you e. So it'd be somewhere like right there. So like I said, just your run-of-the-mill exponential function looks something like that. And then you've got the natural log function, which is the inverse of that. Okay, so the inverse is called the natural log function. So that is an L and then an N. I think it's French, what it comes from. I think it's like logarithme naturel or something like that. You know how in different languages they always put their adjectives before their nouns. So that's why this is LN instead of NL, which is what you might expect. So remember, all logarithmic functions, so this is the same as log base E of x. So all logarithmic functions have this point right here. And then you also have the point, remember, base and then 1. So we also have the points e and then 1. But our log functions all look like this. And we've had experience with log functions before, so we know what they look like. And remember, just a quick little reminder from inverses, anytime you look at a function and its inverse, they are reflections of each other over that diagonal line. So you can see if you were to fold one over the diagonal line, it would land right on the other one. All right, so that is our exponential function with base e. This is our logarithmic function with base e. Just a quick picture just so you can see. Okay, now let's talk about writing back and forth between exponential form and logarithmic form. Okay, so this one, we know how to turn these back and forth. So we write log base e, and then we switch the other two. Of 9 equals x. Okay, so we're never going to write log base e. We're always going to write natural log. So we're going to write natural log of 9 equals x. Just like with the common log, we don't write log base 10, we just write log. So we've got a specific new way to write log base e. Okay, same thing with this one. When we're turning from exponential into log, we start with log base e of x equals 7. But again, we write natural log. So natural log of x equals 7. That's your answer for that one. Okay, so that's going back and forth between exponential form to logarithmic form. So now we're going to go the opposite direction, from logarithmic form into exponential form. Okay, so remember, natural log actually has a base e. So we write down our base e. The thing on the other side of the equal becomes our power. And then we set it equal to whatever we have inside our log function. We've done this multiple times with different bases. It just seems really weird because we're doing it with base e and we don't really understand yet what e is. Okay, so one more here. Remember, natural log is log base e, so we start with the base e, raise it to this number on the other side, and then set it equal to whatever is on the inside of your log function. Okay, so just your run-of-the-mill conversion between log form and exponential form and vice versa. Okay, so the next thing is we're going to talk about some of the properties. So basically, with this section, we're taking all of the stuff that we've done in Chapter 7 so far and just changing it a little bit with our new base E. Okay, so this next thing that we're going to look at is some of the properties. Okay, so I am going to write them just really quickly. Write them if you want. Don't write them if you don't want. I just want to have them right here to reference. So this is the first property. If you've got a product on the inside of a single log, you can write it as the sum of two separate logs. If you've got a quotient on the inside of a single log, you can write it as the difference of two separate logs. And then the third one, if you've got a log expression and your base has an exponent, you can move the exponent out front and write it as a coefficient. Okay, just like that. So like I said, I just want to have them there for reference so that when doing these properties, we can look right back at them. So we want to write each one of these expressions as a single log term. So we're taking these big expanded out log expressions and we want to write them in condensed form. So basically, we are looking at the right-hand sides of these properties and seeing how we can apply these properties to these expressions right here. Okay, so the first thing is notice we've got coefficients out front. We have a 6 out front right here. We have a 2 out front right here. Hopefully when you see coefficients out front, you think of the third property. And the third property, right now it looks like this. We want it to look like this, which means whatever coefficient is right here, we're going to move it inside as an exponent. So instead of the 6 being out here, we're going to write it as an exponent on the 8s. Minus, and then instead of the 2 being right here, we're going to write it as an exponent on the 4. Next, you see we have subtraction. We've got two separate logs and they're being subtracted. Hopefully that leads us to our second property right here. Two separate logs and they're being subtracted. So what that tells us is we can take the two inside pieces, the A and the B, and divide them like this. So that tells me I can take the 8 to the 6th and divide it by the 4 squared. Okay, now that whole thing is now technically inside of my natural log function. And remember, natural log is log base E. So I'm just going to plug this in, the 8 to the 6th. I'm going to do a fraction. I'm going to plug the 8 to the 6th over 4 squared, just so I can get a simplified number for that. And I get 16,384. Okay, so this is the natural log of 16,384. And one really quick way to check if you did it correctly is you want to see if this has the same value as this. So first you can plug this in. 6 times, now the natural log button, I just showed you where the E button is. The natural log button is right above it. So you hit Control first, then that button of 8 minus 2 times the natural log of 4. So that's the decimal value we get for that. Let's test the decimal value we get for this. Okay, so natural log of 16,384. Now notice we get the exact same thing, which means our answer is right. Okay, let's look at another one. So we're going to do the same things. We're going to see these values right here. Those values, we want to move them inside as exponents. Okay, so we're going to take the natural log of 5 squared plus the natural log of 2 to the 4th. And then this one, there's no coefficient to move inside. We'll come back to that step in just a moment. Okay, so this 2 and this 4, according to this property right here, I moved the m, or whatever it was, the 2, the 4, inside as a coefficient. Okay, now next, notice they're all being separated by addition. This one plus this one plus this one. And hopefully that draws you to the first property. If you've got separate logs and they're all being added together, you can take the inside stuff and multiply it in a single log. So this is going to be natural log of 5 squared times 2 to the 4th times 5 times y. So I'm going to put parentheses here just to emphasize to you that all of that stuff is inside of the natural log function. Okay, so to get the coefficient, I want to multiply 5 squared times 2 to the 4th, and then times 5 to know what I should have in front of the y. And that is 2,000 exactly. That's convenient. So natural log of 2,000 y. Now, unfortunately, this one I cannot test in my calculator because I can't plug in a y. So natural log of 2,000 y, that is my whole inside function. Okay, so those are a couple of the properties. All right, so like I said, we're kind of bouncing around in a bunch of different topics. The unified topic that we have here is just using this base of our new number, quote-unquote number, e. All right, so the next thing, we're going to take a look at some special natural logs. Anytime you see the natural log of e, if it's just an e and there's nothing else in there, remember natural log is the same as log base e. So if we have log base e of e, I'm hoping, even if we don't really know what e is, I'm hoping we recognize that if these two match, it's just going to be equal to 1. We've seen that with like log base 4 of 4 or log base 12 of 12. So why should e be any different? Log base e of e is still going to be equal to 1, and that's exactly what the natural log of e is. Okay, natural log of 1, anytime you see that, remember that's really equal to log base e of 1. And again, I'm hoping we recognize this one too. This is saying, all right, my base is e. E to what mystery power gives me an answer of 1? So e to what power gives me 1? Well, the only power that gives me 1 is 0. Okay, so the natural log of 1 is 0, just like log base 2 of 1 is 0, just like log base 10 of 1 is 0. Anytime that your input is a 1, the power that you get out is 0. Okay, and last one. Let's say I have anything as an exponent, like an a. This one, I can actually apply this property right here that tells me if I have an exponent, I can move it out front. So I can take this exponent of a, and I'm going to move it out front, times the natural log of e. And then remember, what's the natural log of e? Well, it's 1. So this is the same as a times 1, which we know is equal to a. So if we had the natural log of e squared, it would be 2. Natural log of e cubed would be 3. Natural log of e to the 12th would be 12. So these are just a couple patterns that you should hopefully have memorized so when they come across, you recognize them and you're able to do them very, very quickly. Okay, so now let's look at some equations and inequalities. We've seen these exponential functions. We've seen logarithmic functions. We've solved these equations before. Like I said, the only difference here is that we are working with exponential functions exponential base e rather than any other normal number base. Okay, so this, we are going to try to get the x by itself. So a couple of our steps are going to be a little bit different. So trying to get the x by itself is actually pretty similar to doing most of the algebra problems that we've seen so far. We're going to start with this one by adding 12 to both sides. And so we'll get 3 e to the 4x is equal to 15 plus 12, which is 27. Then the next thing we're going to do, since, like I said, we're trying to get the x by itself, is we're going to divide both sides by 3. We're trying to strip away, the addition, subtraction, multiplication, division. So these 3's will cancel, and this becomes e to the 4x is equal to 27 divided by 3, which is 9. Okay, so now here's the part that's new. When I had exponential functions that we were doing a couple days ago, we would take the log of both sides. Now in these ones, and this only happens when we have base e. If we have base e, we are actually going to take the natural log of both sides. So we're going to take the natural log of the left, and we are going to take the natural log of the right. So like I said, our normal step is to take log base 10, but only in this unique situation where I'm dealing with e's am I going to take the natural log of both sides. Okay, so now let's apply the power property, where this 4x can come out front as a coefficient. So now I have 4x times the natural log of e equals the natural log of 9. Okay, now take a look at this left-hand side, natural log of e. Like I said, I am hoping that when you see this, you recognize it as just being equal to 1. So if this is just equal to 1, then my left-hand side is just equal to 4x. Okay, then the very last thing I'm going to do to get my x by itself is divide both sides by 4. Okay, now be very, very careful here. Make sure you're taking the natural log of 9, whatever that is, closing off the parentheses, then dividing by 4. If you divide the 9 by 4, you'd get a very different answer. Okay, so this is my approximate answer. It said round to the nearest 10 thousandths, which means 4 decimal places. So 0.5493. Okay, let's look at another one really quickly. Same sort of steps. We're going to start by subtracting 8 from both sides. And we get 9. And then we're going to divide both sides by 4. So these cancel. So we get e to the negative x equals 9/4. And then we're going to take the same step that we did last time. Once we get this exponential part by itself, we are going to take the log of both sides, but because I'm dealing with e rather than any other number, I'm going to take the natural log of both sides rather than the common log of both sides. Okay? I can also use this property to tell me that if I have the natural log of e to the something, it's just equal to whatever that something is. So if I have natural log of e to the negative x, it's just equal to the negative x, which is exactly what happened here. I had a 4x in my power, and it ended up just equal to 4x. On the right-hand side, I have the natural log of 9/4. And finally, I'm going to multiply both sides by a negative. And when I plug that into my calculator, that will be my answer. It's the negative natural log of 9 divided by 4. Okay, so same thing to the 10 thousandths, which means 4 decimal places. So negative 0.8109. Okay, so that's one version of my equations that we're going to be looking at. The other is with natural log. And so it's going to be the opposite. Rather than looking at exponential functions and using logs to simplify, we are going to look at logarithmic functions and talk about exponentials in order to simplify. So the way that we solved natural log functions before was by turning it into exponential form. So we did this on the front page as a little bit of practice. So you should be able to pretty quickly turn back and forth between logarithmic form and exponential form. Okay? With these, the first thing we're actually going to do though is clear out that 5. So divide both sides by 5. And we have the natural log of 6x equals 8 divided by 5. Okay, then like I said, the next thing we're going to do is turn it into exponential form. So natural log is log base e. So I'm going to take my base, raise it to the power, and then set it equal to 6x. This is just converting back and forth. This is logarithmic form. This is just converting it into exponential form. And once I convert it into exponential form, I'm that much closer to having the x by itself. So all I have to do is divide both sides by 6. Okay, and then that can just go right into my calculator. I will show you. So here's our e button. We do e to the 8/5, and then divide that whole thing by 6. Okay, make sure you're dividing the whole thing by 6, not just the 8/5. Okay, so 4 decimal places, so about 8255. Okay, now we can quickly look at an inequality here. So the inequality is set up basically the same way. The only issue is that we need to make sure that the inside stuff is going to be positive. All right, so with this, we are going to start by converting it into exponential form. All right, so we've got e to the 6th is greater than 2x minus 3 cubed. And then we're just going to make sure at the ends that we don't end up with any negative values inside of our log function. Okay, I'll come back to that in a moment. Now we're going to do whatever math we need to do to get that x by itself. So this part's a little weird. We got to take care of this cubed power first. So we are going to cube root both sides. Okay, so we're going to cube root the right, which means we've got to cube root the left. Okay, so on the right-hand side, those two things just cancel each other out, and all I have left is a 2x minus 3. And then the cube root of e to the 6th. Cube root of e to the 6th. Let's actually, the cube root of e to the 6th is the same as, do you guys remember doing this? Writing it like that. The fact that you've got this 3 right here means it's the same as taking a cube root. And so the 6 over 3 actually reduces down to e squared. So this left-hand side is now just an e squared. Okay, now just a couple more algebra moves. I am going to add the 3 to both sides. So I have e squared plus 3, whatever that is, and I'll use my calculator in just a moment. And then finally, to get the x by itself, we're going to divide both sides by 2. Okay, so these are going to cancel out. Now I'm going to write it in reverse order. I'm going to write x is less than this. I'm going to plug this into my calculator. So a little fraction, e to the 2nd power plus 3, divide that all by 2, and we get this value. Okay, about 5.1945. Okay, so that's our starting value there. And then we've got to make sure that we're not plugging in anything that would make this smaller than 0. So we're going to take the 2x minus 3, and we're going to make sure that it's always bigger than 0. Okay, so let's add 3 to both sides. Divide by 2. And I get x is greater than 3/2. Okay, so not only does x have to fall into this category, it has to be bigger than 3/2 as well, which means so I can say x has to be bigger than 3/2 or 1.5, and that would be your final answer. All right, so we are actually going to cut there. We just crossed over into 22 minutes, and I think that you guys have probably had enough of this.